Hello, my name is Thomas Powers, and this is my Project 1 for Design and Manufacturing for Dr. Hassan Rashidi. My project is called Top 5 Engineering Strategies. So, a little about me first. Engineering is all about solving complex problems and bringing ideas to life. Through my personal experience working on nuclear submarines, drones, and rockets, I've seen firsthand how design and manufacturing methods can make or break a project. Whether it's ensuring structural integrity of a vehicle, optimizing the manufacturability of a drone component, or improving reliability and human safety in nuclear reactor systems, the right engineering tools can be the difference between success and failure, sometimes even in citizens' lives. In industries like aerospace, defense, and advanced manufacturing, every decision we make must balance performance, efficiency, and cost. That's why I've chosen these 5 engineering methods that I believe are fundamental to designing and manufacturing better products. First, we have design for manufacturability. Second is additive manufacturing or 3D printing. Third is failure modes and effects analysis, aka FMEA. Fourth is lean manufacturing and Six Sigma. And the fifth and final one is finite element analysis or FEA. So first up is design for manufacturability. A summary is that it's a product design philosophy that optimizes a component or system for efficient manufacturing. The goal is to minimize cost, improve quality, and of course, reduce complexity. And here are a couple examples. In aerospace, DFM helps reduce part count and weight, improving fuel efficiency. In the automotive industry, it enables mass production of standardized, easy to assemble parts. And in medical devices, it ensures components meet regulatory standards. In terms of importance, capabilities, and limitations, um, it, it reduces production, improves manufacturability, ensuring the design can be efficiently produced with minimal defects, and it also reduces lead time in production, accelerating the time to market. So in terms of capabilities, it simplifies assembly. It also enhances product reliability by eliminating weak design points, and it also reduces material waste, making the process more sustainable. And of course, like everything, it has its limits. It can restrict design freedom, requiring some trade-offs, and also requires early collaboration between everyone on the different teams, which can make it challenging in larger teams or larger companies. The second is additive manufacturing or 3D printing. It builds objects layer by layer using digital models, typically plastics as well. This allows for creation of complex geometries that traditional manufacturing methods are typically really difficult to produce or even impossible in some cases. So its use cases in aerospace, GE uses it. They actually do metal 3D printing. In the medical industry, they custom print prosthetics and implants or even skin grafts for they're customized for individual patients. In the automotive industry, companies like Ford use it for rapid prototyping of vehicle components so that they can test a component before they actually shell out more money to test it in the field. Importance, capabilities, and limitations. First up, importance. It enables rapid prototyping, reducing the development time by a lot. Allows for complex designs without requiring specialized tooling because you only need one 3D printer. And then it reduces material waste compared to subtractive manufacturing processes. Like if you have a block of metal and then you need to make a part, you're shaving off all the metal. But when you're 3D printing, you're only using the material that you need to make the part and nothing extra aside from like supports. Some capabilities is that it can create intricate geometries impossible with traditional machinery. It's highly customizable and also reduces material waste. Some limitations include slower than mass production techniques, limited material options, and post-processing may also be required to achieve like final part quality if you want a super smooth finish or you want it to have a certain feature that you wouldn't be able to do on the 3D printer itself. Third is failure modes and effects analysis or FMEA. It's a systematic approach used to identify potential failure points in a product, process, or system before they occur. It assigns a risk priority number to each failure mode based on severity, occurrence, and detectability. And some applications include NASA in the aerospace industry uses it for spacecraft reliability to prevent catastrophic failures like the Challenger disaster. After the Challenger disaster, this technique and others like it were heavily increased at the company to make sure that to reduce the risk of that happening again. In the automotive industry, it's used in crash design safety to analyze potential failure points and in the medical industry, it ensures life-critical equipment are reliable. In terms of importance, capabilities, and limitations, first off, it helps engineers proactively address design flaws before costly failures occur, obviously saving the company a lot of money. It ensures compliance with safety standards, which is important for legal reasons. It also reduces warranty claims and liability risk by improving product reliability. Some capabilities include preventing costly failures, uh, again, helping in the quality control, and then enhancing customer satisfaction by ensuring reliability, which is probably one of the biggest points. It does have its limitations, of course. It's really time consuming and requires thorough analysis. It also relies on accurate failure data, which may not always be available, or sometimes companies try to do this with inaccurate data, which doesn't really mean anything at the end of the day. And then it also does not account for unknown or unforeseen failure modes. So the fourth is lean manufacturing for Six Sigma. I actually have a green belt certification in this. It was about a day class, and I earned it during my quality control engineering internship at Viasat in Duluth, Georgia, a few years ago. And my team was all about Six Sigma. We used it and the techniques along with it every single day to do root cause analysis on components. My main job was figure out the root cause on why specific testing centers were failing, and I use Six Sigma. So a summary is that lean manufacturing focuses on reducing waste and inefficiencies, and Six Sigma itself is a data-driven approach to minimizing defects and improving quality. And when they mesh together, that's when they create highly efficient manufacturing environments. Excuse me. So some applications. First off, Toyota uses it to reduce overproduction and waste. GE uses it in aircraft engine manufacturing to achieve near zero defects, which is really important for safety and also very impressive. And then in the electronics industry, it reduces variability in semiconductor manufacturing, making sure that each product is as close to spec as possible. So the importance is it eliminates waste. Obviously, that saves costs. It improves quality, which is better for the customer, less broken parts, and also enhances efficiency, leading to faster production cycles. Some capabilities include reducing the lead time, enhancing process control and consistency, and then obviously product quality and reduce cost. So the limitations include a cultural shift, which can be difficult to implement because you have to basically install whole new processes in place to ensure that you're meeting these numbers. It's always not suitable for small scale or highly customized manufacturing because it would take way too long to adapt that to such a small scale. And then it can be resource intensive to train employees in Six Sigma methodologies. You have to pay for the course. They have to take like days or even weeks if they want to get all the way through the course, stuff like that. The final one is FEA, or finite element analysis and design. So it's a numerical simulation technique used to predict how a part or structure will behave under various conditions, and it's widely used in engineering to analyze stress, strain, thermal, and vibrational effects, along with others. So it has its applications in aerospace, automotive, civil engineering, and really any field where you're designing something that's going to be put under loads or stress or temperatures. In aerospace, Boeing and SpaceX use it. Automotive engineers analyze crash worthiness and material behavior so they can simulate, let's say, a car crashing without actually having to test it. And then in civil, they use it to simulate bridge loads and structural integrity under like varying loads over time. Some importances are it reduces reliance on physical testing, saving time. It allows engineers to optimize designs, and it helps identify weak points and improve material selection. It's also high accuracy. It can simulate a wide range of conditions, like I said before, and it enables virtual testing, reducing physical prototype costs, as in the car. Limitations include significant computational power. A lot of times it requires supercomputers. Results are only as accurate as the input parameters and assumptions, which you have to get correct. And then it may not fully capture real-world complexities like material imperfections. And I did FEA in my internship at Naval Nuclear Lab on the reactor itself. Here are my sources. So, in conclusion, mastering these methods doesn't make us better engineers, it makes us more effective problem solvers. Whether it's improving safety in nuclear systems, increasing reliability in rocket components, or streamlining drone manufacturing, These tools help bridge the gap between innovative design and real-world production.